Okay, here we are for lesson 2, the formal definition of a function. So the materials you're going to need for this lesson is a calculator to calculate some exponential calculations. So this lesson continues the work of example 2 from lesson 1, leading to a formal definition of a function. Remember what we learned about functions from lesson 1. The purpose would be to abstract the information in example 2, specifically that in order to show all possible time intervals for the stone dropping, we had to write the inequality for time as t, or for time t as t is greater than or equal to 0 or less than or equal to 4. Alright, let's take a look at the opening exercise, which you're going to do in your journal. Shown below is a table from example 2 of the last lesson and another table of values. Make a conjecture about the differences between the two tables. What do you notice? Alright, so using the table on the left, state the distance that the stone traveled in 1 second. You should have said after 1 second the stone traveled 16 feet. Using the table on the right, state the distance the stone traveled in 1 second. Well, after 1 second the stone traveled 4 or 36 feet. And you can see that here. There are two 1 seconds. One is for 4 and the other one is for 36. So which of the two tables above allows us to make predictions with some accuracy? Well, the table on the left seems like it would be more accurate. The table on the right gives two completely different distances for the stone after 1 second. We cannot make an accurate prediction because after 1 second, the stone may be either 4 feet from where it started or 36 feet. So we will define a function to describe the motion given in the table on the left. The importance of a function is that once we define it, we can immediately point to the position of the stone at exactly t seconds after the stone's release from a height of 256 feet. It is the ability to assign or associate the distance the stone has traveled at each time t from 256 feet that truly matters. So let's formalize this idea of assignment or association with a symbol d, where d is used to suggest the distance of the fall at time t. So d assigns to each number t, where t is greater than or equal to 0 or less than or equal to 4, another number which is the distance of the fall of the stone in t seconds. For example, we can rewrite the table from the last lesson as shown below. That for each t in seconds, notice that we're not calling it x anymore, we're calling it t, since that is what we're concerned with. T seconds is going to be assigned a feet traveled, which is going to be y, or our dependent variable. We can also rewrite it as the following table, which emphasizes the assignment the function makes to each input. So the function d assigns 4 to half a second, or this would be 4 feet to half a second. D also assigns 16 feet to 1 second, and so on and so forth. Think of it as an input-output machine. You've probably done these in 4th, 5th, or 6th grade. That is, we put in a number, the input that represents the time interval, and out comes another number, the output, that tells us the distance that was traveled in feet during that particular interval. So we can pick any time t between 0 and 4. When we plug it into our function, then we get a distance traveled in that amount of seconds. With the example of the falling stone, what are we inputting? Well, the input would be the time interval. And what is the output? The output is the distance the stone traveled in the given time interval. So if we input 3 into the machine, what is the output? The output is 144. And if we input 1.5 into the machine, what is the output? Well, the output is 36. Of course, with this particular machine, we are limited to inputs in the range of 0 to 4 because we are inputting the time it took for the stone to fall. That is, time t, where t is greater than or equal to 0, or less than or equal to 4. The function d can be expressed by a formula in the sense that the number assigned to each t can be calculated with a mathematical expression, which is a property that is generally not shared by other functions. Thanks to Newtonian physics, you know, Isaac Newton, the apple falling on your head from a tree, for the distance traveled in feet for a time interval of t seconds, the function can be expressed as the following. Distance for the time interval t is equal to 16 times t squared. From your work in the last lesson, recall that you recognized 16 as a factor for each of the distances in the table below. So for 1 second, it was 16 feet. For 2 seconds, it was 64. 3 seconds was 144. And 4 seconds was 256. Functions can be represented in a variety of ways. At this point, we have seen the function that describes the distance traveled by the stone pictorially, from Lesson 1, Example 2, as a table of values and as a rule. We could also provide a verbal description of the movement of the stone also. Alright, so exercise 1 on your lesson worksheet. Use your calculator to complete the table in exercise 1 and answer parts A and B. Continue the video when you are finished. Okay, you should be done with exercise 1. Go ahead and compare your answers to the ones listed here. If you have any questions, make sure you make a note and bring it to class to discuss. Alright, let's go ahead and discuss exercise 1 using your journal to take notes. Being able to write a function or a formula for the function has fantastic implications. It is predictive. That is, we can predict what will happen each time a stone is released from a height of 256 feet. The function makes it possible for us to know exactly how many feet the stone will fall for a time t as long as we select a t so that t is greater than or equal to 0 and less than or equal to 4. Not every function can be expressed as a formula. Imagine being able to write a formula that would allow you to predict the correct answers on a multiple choice test. That would certainly come in handy. But now that we have a little bit more background on functions, we can define them formally. The definition of a function is a rule or formula that assigns to each input exactly one output. So let's examine that definition more closely. A function is a rule that assigns to each input exactly one output. Can you think of why the phrase exactly one output must be in the definition? Well, using our stone dropping example, if d assigns 64 feet to 2 seconds, that is, the function assigns 64 feet to the time interval of 2 seconds, would it be possible for d to assign 65 feet to 2 seconds as well? Well, it would not be possible for d to assign 64 and 65 to 2 seconds. The reason is that we are talking about a stone dropping. How could the stone drop 64 feet in 2 seconds and 65 feet in 2 seconds? The stone cannot be in two places at once. In order for functions to be useful, the information we get from a function must be useful. That is why a function assigns to each input exactly one output. We also need to consider the situation when using a function. For example, if we use the function distance for time interval t is equal to 16 times t squared, for for t to equal -2, then it would make no sense to explain that -2 would represent 2 seconds before the stone was dropped. Yet in the function, when t is equal to -2, we come up with an answer. The answer is 64. But again, we could conclude that the stone dropped from a distance of 64 feet 2 seconds before the stone was dropped. Of course, it makes no sense. So similarly, if we use a formula to calculate the distance when t is equal to 5, we would get 400 feet. So what is wrong with this statement? Well, it would mean that the stone dropped 400 feet in 5 seconds, but the stone was dropped from a height of 256 feet, so again, that makes no sense. How can you fall 400 feet when you're only 256 feet above the ground? To summarize, a function is a rule that assigns to each input exactly one output. Additionally, we should always consider the context, if provided, when working with a function to make sure our answer makes sense. In many cases, functions are described by a formula. However, we will soon learn that the assignment of some functions cannot be described by a mathematical rule. The work in Unit 5, or Module 5, is laying a critical foundation for our understanding of functions in high school. So what we're going to be doing is just doing some basic work in functions, but this will really lend itself to Algebra 1, Algebra 2, and this is also the beginnings of calculus. All right, next do exercises 2 through 5. Use your calculator to complete the remainder of the exercises and then continue the video when you are finished. All right, so check your answers. If, again, you have any questions about your answers matching the answers listed here, please make a note and bring them to class. One note is for number 5, part B, notice how the rate is written as a fraction. Again, we do not want to have this as a rounded decimal, and anything with 17 as a denominator is going to have a very long repeated type of decimal. So the common and more accepted form is to leave it as an exact answer, which would be in the fraction format. All right, let's wrap this up. We know that a function is a rule or formula that assigns to each input exactly one output. We know that not every function can be expressed by a mathematical rule or formula. The rule or formula can be a description of the assignment. We know that functions have limitations with respect to the situation they describe. For example, we cannot determine the distance of a stone dropping in -2 seconds. Functions are sometimes described as input-output machines. All right, we'll see you in class.